Hello dear students, welcome back to my channel. So in this we are discussing electrolytic conductance, lecture 8. Earlier we have discussed electrochemical cell, Faraday laws, related problems, Nernst equation, everything clearly. If anybody not watched the previous videos, just watch, surely it will help so that even this can understand better. Let's start how. So it mainly deals with movement of ions in solution and explain the ability of electrolyte to conduct electricity is nothing but electrolytic conductance. Coming to what is electrolyte. So in this starting we discuss related terminology. So an electrolyte is a substance that produces ions in aqueous or molten state and conduct electricity. Produce ions in aqueous or molten state and conduct electricity. So here based on the dissociation or degree of dissociation or alpha value, we can segregate electrolytes are into two types: strong electrolytes or weak electrolytes. So alpha value nearly is 1, means whatever the electrolyte you take, that completely dissociate into ions, because alpha is nothing but number of moles taken number of moles dissociated by number of moles taken initially. So whatever the moles of electrolyte we took, that completely dissociate. So this together is same, means alpha is 1. So weak electrolyte means the alpha value is approximately 0.1. That means only 10% of electrolyte is going to dissociate. So examples for this: all strong acids, strong bases and salts, NaCl, HCl, NaOH, all this. Weak electrolyte examples: weaker acids and bases are organic acids and bases. Some of the inorganic also, like H2CO3 or HCN. So mechanism of, or just we are going to start terminology in this. So after this we can discuss what are the types of conductors. So difference between metallic and electrolytic conductors. Metallic conductors means electric current is carried by the free ions. Electrolytic conductors means the current is carried by the ions. This is also called as ionic conductors. This is called as electronic conductors. Electronic means through electrons conductivity happens, but here through ions conductance happens. So conduction doesn't involve any chemical change because it related to electrons. Conduction is always happened by the chemical reactions because the chemical itself converted into ions. So example, all the metals. Here examples, ionic electrolytes. Conductivity decreases with increasing temperature because conductivity decreases with the temperature. The reason behind that, the electrons will vibrate instead of flow when temperature of the metal increases, so that resistance increases when temperature increases, conductance decreases in case of metallic conductors. But in case of ionic conductors, the salt will split into ions more when the temperature increases. When ions are more, that go and deposit over the respective electrode. Due to that movement of ions, the current or electricity will generate. So flow of current doesn't cause decomposition because matter won't involve in this. Flow of current causes electrolysis. Electrolysis means more the dissociation, more the conductance. Resistance is mainly due to collision of electrons with lattice ions. So same ions will repel, if opposite ions means it will attract. Resistance is due to inter-ionic attractions. Sorry, here resistance is mainly due to collision of electrons, because electrons only main current carriers in case of metallic conductors. But resistance means here ions will decide. So conductivity is independent of concentration, because it's no matter involved in this metallic conductors. Conductivity depends on the mainly concentration of electrolyte. This is very important point. Based on this, we'll discuss some of the things. No transfer of matter occurs. Ohm's law is followed strictly. This also Ohm's law is not followed strictly all the cases. So here Ohm's law followed strictly, here not followed all the cases. Transfer of matter occurs at electrodes. That's what deposition or liberation. Here no transfer of matter because it happens through electrons. These are the differences between metallic and electrolytic conductors. Now we are going to start the related terminology in this. Hope it is clear, students, until this. So coming to first one, resistance. So resistance indicated with capital R. Resistance is defined as the opposition offered by the solution to the flow of electric current. So this R is directly proportional to L by A. Here L is nothing but length of the solution or conductor in normal case. A is area of cross section. This you already studied in physics, so this is easy. And it also depends on the nature of electrolyte. So here R is equals to rho L by A. Here rho is nothing but conductivity or rho is nothing but resistivity. It is constant for particular object or particular metal. L is length of the solution. R is area of cross section. So here length we can also tell it as the distance between two electrodes of the electrolytic cell. So R is nothing but resistance. The units of resistance is SI unit is ohm. This we can indicate like this. So other unit is mho inverse. And coming to next, second term, conductance, indicated with capital G, which is the reciprocal of resistance. So G equals to 1 by R. SI unit will be Simon. So Simon inverse is also one of the unit for R. So mainly this depends on, means conductance depends on the dimensions of solution. This is very very important point. We will discuss. Questions mainly asked from this only. So this is about conductance. Next is cell constant. So this indicate generally with G star. It is the geometry of conductivity cell, or it is defined as distance between electrodes versus electrodes upon area of cross section. It is the ratio of distance between electrodes to area of cross section. So G star equals to L by A. So here L is length or distance between electrodes, R is area, A is area of cross section. So this cell constant mainly depends on the cell, not on the solution. Not on the solution. Units we can write. L is centimeter suppose, or meter if you take. This will be meter square, which can be written as meter inverse, as like this. Coming to next, specific conductance, which can be written as kappa, also called as conductivity. This can be defined as, it is the conductance of one centimeter cube of electrolytic solution. So here, conductance of solution of unit length and unit cross sectional area. So 1 centimeter cube means length will be taken as centimeter and area of cross section is centimeter square. Whatever the electrolyte present in this volume, that conductance we can call it as conductance or specific conductivity. Sorry, specific conductance or conductivity. So SI unit will be, so here K we can write it as 1 by rho. We can also tell the same thing. It is reciprocal of resistivity. Reciprocal of resistivity is also called kappa. So SI unit we can tell it as R equals to rho into L by A. If you want rho here, RA by L. So that ohm meter square by meter if you take, what you will get, ohm meter you will get. Or also call it as Simon. So this is the unit, ohm meter. So most important formula based on conductance, which is G, cell constant G star, and conductivity or specific conductance kappa. This is most important formula. So here G can write it as 1 by R. G star is nothing but cell constant L by A, and kappa is nothing but specific conductance, which can be written as rho. So these are the most important formulas. So this specific conductance or kappa decreases over dilution, because over dilution the number of ions decreases per this much volume of the electrolyte. So when we start adding water, the ions of the electrolyte coming out from this volume, so indirectly number of ions decreases at particular volume. That's why over dilution kappa value decreases. So the ions per unit volume decreases. The reason is the ions per unit volume decreases. So the same thing increase with temperature. The reason is higher the ionic mobility. If you increase temperature, mobility of ions increases. That's why specific conductance will increase. Coming to next one, molar conductance, which can be indicated as lambda m. Molar conductance is the conductance of all ions produced by 1 mole of electrolyte. Conductance of all ions produced by 1 mole of an electrolyte. So indicated with lambda m, and this mainly depends on concentration. SI unit will be Simon meter square mole inverse, because lambda m can write it as kappa into 1000 by molarity or concentration. So here kappa means specific conductance, molarity is moles per liter. So effect of dilution, is dilution increases lambda m increases due to increasing distance from the ions, which means if the distance increase from the ions, suppose if you take Na plus and Cl minus, if distance increase because of more addition of water, these two will be away from each other like Na plus and Cl minus, so that moment will increase. So when moment increases, the conductance also increases. So there will be no boundary for the molar conductance, so that the internuclear distance or interionic distance will increase. Interionic distance increases, so that the molar conductance increases. That's what the molar conductance and the dilution effect. Next one, equivalent conductance. This can be indicated as lambda eq. Same type of definition. The conductance of all the ions produced by one equivalent of electrolyte is called as equivalent conductance. So lambda eq equals to kappa into 1000 by normality. So we know the relation between normality and molarity. Normality equals to molarity into n factor. Since normality or molarity in the above formula at the denominator, so we can make the relation lambda equivalent into n factor equals to lambda m. This is most important formula. So based on this, many questions are asked. And here units, what you can write is units of this Simon centimeter square and equivalent inverse. This is the formula for equivalent conductance. So here dilution increases lambda equivalent also. Same reason like above. So there is one more thing, lambda m naught limiting molar conductance, which also tell it as limiting molar, it is also called as molar conductance at infinite dilution. So limiting molar conductance is nothing but the molar conductance at infinite dilution. At infinite dilution, that's the reason if you put lot of water, the concentration negligible, so that it is written as not at superscript. So at infinite dilution, what happens? Interionic interactions become negligible. So if interactions decreases, the moment will increase. Negligible. Ions move independently. It has a definite maximum value. So in the next class, we are going to discuss the additional problems, Kohlrausch's law and Debye-Onsager equation. Let's start the questions of these formulas. The first question is, resistance is given, cell constant given, concentration is given, and asking what is kappa or specific conductance. Asking lambda m value or molar conductivity. So what are the given values here? G star is given, which is 1.14, which is called as cell constant, and R value resistance is given 1500 ohm, and concentration is given, which is called as 0.001 m, molarity also, and temperature is given 298 kelvins. And first what we have to do is, they are asking lambda m kappa into 1000 by molarity, but kappa you cannot get directly because they didn't give that. So kappa you can find based on G into G star. So here G is not given directly. In the place of G, what you can write? 1 by R. So kappa equals to 1 by R means G star by R you can write it, which is called as cell constant by R. So first we will do that. K equals to, that is kappa equals to 1.14 is cell constant or G star by 1500 ohms, which is R. So if you simplify this, you will get 7.6 into 10 power minus 4 Simon centimeter inverse. This is the which one kappa value. Now we can use this formula to find the lambda m. So lambda m equals to 7.6 into 10 power minus 4 into 1000 by, this one is 10 power 3, which can be written as 7.6 into 10 power this, sorry, minus 3 it is. So if you send up, it will be 10 power 6 into 10 power minus 4. So that we can write it as 760 Simon centimeter square and mole inverse, because that is molar conductivity. So this is the answer, students, for this question. So this question came in JEE Means 2021. Hope it is clear. Coming to second question. So here what they are asking, just conductivity of mercury at 0 degrees is this one, and the resistance of the cell is this many ohms. In cell constant they are asking. So it is direct formula based and simple also. So we know that G star into G equals to specific conductance. So what are given values we can substitute here. So kappa value is given 1.07 into 10 power 6 Simon meter, and R value is given 0.243 ohm, and they are asking cell constant, which is G star. Cell constant is nothing but G star. So we know that G equals to 1 by R. Just substitute that in this formula, and what you can get, it is G star equals to K by G. Here we know that G equals to 1 by R. So G star equals to K into R. So K into R, if you substitute, what you will get is, so 1.07 into 10 power 6 into 0.243. If you simplify this, you will get 2.6001 into 10 power 5 meter inverse, because it is G star, right? G star unit is L by A, means meter inverse only will get. So this we need to express in this format, x into 10 power 4 meter inverse. So what can be written in this? So this is 10 power 5 it is. So if you want to write 10 power 4, 26.001 into 10 power 4. This is the answer for this question. Hope it is clear, students. Direct formula based, but calculation take little more time. Next one, KCl solution conductivity is given, shows the resistance also given in conductivity cell. If same cell, means G star mainly depends on cell, not about the solution. So HCl solution, the resistance drops to 1.03 ohm, the conductivity of HCl solution. So here what we have to do is, first we should calculate G star from the first cell, that need to substitute in the second cell and find the kappa value. Hope it is clear. Because two cells, first you need to calculate G star from the first conditions of resistance, and another one is specific conductance or conductivity. First we have to calculate G star by using conductivity and resistance of first solution. That calculated cell constant should use in the second cell. So what we have to write, just write the given values first. So kappa value is given, kappa of KCl is equals to 0.14 Simon per meter, and R value is given for first one, which is 4.19 ohm, and R equals to R of HCl is given, that we can discuss at last, 1.03 ohm. Now from these two we can calculate G. So G into G star equals to R. So sorry, G into G star equals to kappa. So G star equals to K by G. We can also write it as K into or kappa into R, because G is nothing but 1 by R. So Kr equals to G star. First we will do this. What you will get here is 0.14 into R value is 4.19. You simplify this, you will get 0.5866 meter inverse, because cell constant. This calculated cell constant should use in the second cell. So conductivity. So this is first one. This is second step in this problem. Conductivity of HCl means kappa of HCl they are asking. So kappa of HCl, same formula, G into G star equals to kappa. So here resistance also given, no, resistance of HCl will be 1.03. so they are asking this one, right? So G star value is, which we calculated, 0.5866, whatever we got here, that itself G star for second cell, and G into G star equals to kappa. That means, so G value we can write it as, sorry, this value by, for G is nothing but 1 by R, so that G star by R equals to K. So this is 1.03. If you simplify this, you will get 0.5695 Simon meter. Now we have to express in the particular form, which is this x into 10 power minus 2. So if you write this with minus 2, you can get 56.95 into 10 power minus 2. So 56.95 is nearest integer is 57 into 10 power minus 2. So answer is 57. That's how we can do this question. Hope it is clear. See, if they give 2 times, calculate cell constant from first condition, that substitute in the second condition to get the respected answer. Hope it is clear. Yes, students, we'll continue Debye-Onsager equation. Let's start the next topic, Debye-Onsager equation. So before going to this, we will discuss how concentration affect over the molar conductivity. Lambda m increases by decreasing concentration. How it happens even for strong electrolytes we will discuss. See, if you see the weak electrolyte concentration can decrease over addition of water. When we add more water to weak electrolyte, the weak electrolyte dissociation going to rise. So number of ions increases, conductance increases. That's how we can link for the conductance, molar conductivity over the weak electrolyte. But in case of strong electrolyte, how it will work? Because strong electrolytes dissociate 100% without water. But still, over dilution of strong electrolyte, conductance is going to rise. How it happens? So initially itself, the complete electrolyte dissociate and alpha value reaches to 1. When we start adding water to this, the ions go away from each other. So inter-ionic distance between positive and negative ions of electrolyte, that is how the attractions between these two will decrease, so that the moment of ions going to rise. So strong electrolyte molar conductivity increases over dilution because of increasing movement of ions or decreasing inter-ionic interactions. So that itself we can discuss with the Debye-Onsager equation. So before going to that actual Debye-Onsager equation, few more points we can discuss. Electrical conductance in solution depends on number of ions and speed of the ions. speed of the ions. So at infinite dilution, ions are far apart. Ions will move from away to each other, far apart, and no interaction, no ionic interaction or interionic interaction, and mobility reaches to maximum. So limiting molar conductivity and lambda m, if you compare, lambda naught m value is always greater than lambda m value even for strong electrolyte. And lambda m is going to rise when concentration decreases. Here this decrease is not due to ionization but due to interionic interactions. That's what till now we have discussed. This theory mainly based on two effects. The first one is ion atmospheric effect. So what exactly Debye-Onsager equation we can see. Debye-Onsager equation is lambda m equals to lambda m naught minus a into under root c. So here lambda m is molar conductivity at concentration C. This one is molar conductivity at infinite dilution. A is constant, depends on solvent, temperature and electrolyte type. And C is concentration mole per liter, in mole per liter. So here how the graph we can see. The graph, so here root C versus lambda. So here we can write it as lambda naught. Over dilution, the weak electrolyte is not touching to the y-axis at any case. So Debye-Onsager equation is not applicable for weak electrolyte. Means we cannot calculate maximum conductance of weak electrolyte over dilution. But strong electrolyte touching to this y-axis, which means the strong electrolyte have limit molar conductivity over dilution. So this theory is not applicable for weak electrolytes and valid for strong electrolytes. Very important. And it is also applicable at low concentration. Low concentration only we can calculate maximum molar conductivity of strong electrolytes. And lambda m versus root C is straight line graph. Straight line. So intercept is lambda naught. So why it is not applicable for weak electrolyte? The weak electrolyte is not fully ionized at infinite dilution. Conductivity depends on the degree of dissociation for weak electrolytes and follows Oswald dilution law, because alpha term is there, so it is applicable for Oswald dilution law, which you studied in 11th. And if you don't know that, we will discuss in Kohlraasch law completely. And in case of strong electrolyte ionize completely and reaches to maximum value or limit value. Conductivity depends on the interionic forces. Since the ions go away from each other over dilution, so conductivity will be maximum. And follow Debye-Onsager equation. So here slope will be negative because lambda m equals to lambda m naught minus a into under root c. So y equals to c plus mx. That's how we can get negative slope everything. For strong electrolyte, this is the formula. For weak electrolyte, alpha term will come, which is DOD, because weak electrolyte dissociation or conductivity depends on the alpha mainly. So alpha square equals to lambda m by lambda naught m. Can write anyhow. That's the overall, students. Hope it is clear. So next is most important lecture, that is Kohlraa's law and related applications. Must watch that video because questions mainly asked from that only.